Quantum computers are really hard to build. Right? I've been working on this in some form or another for over a decade, so I can say that with some authority. Now, you may know that here at Sussex, we do have a number of prototype quantum computers over in the physics department. And my colleague, Winfried Hensinger, is really proud of these things that we've built and improved on over many years, and rightly so. They've enabled us to demonstrate a lot of the first steps for quantum computing, to probe the limits of the physics underpinning the highly engineered quantum processors we imagine in the future. But if you ask about the performance of the devices we have in the lab today, and in fact, a journalist did recently ask how well they work, and I have the published quote right here. They're all terrible. So, well, we expect these things to get better, and a lot of people are banking on them getting better. If the investment flowing into quantum startup companies and the government funding focused on developing national quantum initiatives is anything to go by. So I'd like to give you an idea of why today's prototype quantum computers, both here at Sussex and in IBM and Google's data centers, various other R&D labs around the globe, are all generally terrible. Right? Why are qubits, these building blocks of a quantum computer, why are they so hard to use without making mistakes? And what can we do about that? As a warm-up, we're going to think about non-quantum or classical computers, right? The information in our phones, our laptops, microwave ovens even, everything in the cloud, it's all stored and processed as binary digits, zeros and ones, just two options for every fundamental unit of information. Why? Well, it's because this is a really simple building block. And despite that, with a lot of them, you really can do a lot. Now, over half a century of research and development, humans have gotten pretty good at building hardware to faithfully represent these abstract zeros and ones. Right? The technology is called the transistor, and you all carry around about 1 billion of them within the silicon chips at the heart of our devices. Now, they generally just work, right? So we don't often worry about the details. But let's take a look. Now, our abstract information is binary, right? 0 or 1. And we often say that a transistor is like a switch, either off or on. But that's a bit of a simplification. In reality, it's more like a tap, right? It can be leaky, and the flow rate can be variable, right? Rather than a tap controlling the flow of water, it's controlling electrical voltage signals on microscopic wires. So let's say that our abstract 0 and 1 are represented by specific voltages of exactly 0 and exactly 1 volts. Right? These are the ideal signal levels. This is a messy, real-world thing, right? A continuous parameter that can be a little bit higher or a little bit lower from time to time or from place to place, right? Because of some unwanted noise or interference. So what do? Well, we set up some thresholds, right? We configure the transistors to generally work so long as the voltage is close enough. Perhaps anything below 0.2 is a 0, and anything above 0.6 counts as a 1. So although the underlying physics of the transistor, this voltage thing, is analog, we engineer it into a digital building block by setting up a margin for error. Now, sometimes this isn't quite enough, right? If there's a bit more noise than usual, a glitch in the power supply, overheating, or some interference, then look what can happen. What should be a high voltage signal drops below the threshold for a moment and could register incorrectly as a 0. And so we come to error correction. The most naive approach is to just duplicate everything. Instead of putting a single 0, we put 5 in a row. Same for 1s. And then if an unlikely error does occur, well, it's pretty simple to spot the erroneous digit and correct the mistake. So this repetition code enables error correction according to a pretty self-evident rule, but this scheme is wasteful, right? It's mostly redundant information. Now, other schemes are possible, and one option is this sort of thing. We'll take a few digits of data, let's say 4 of them. Now we count how many ones, and we'll determine a 5th digit. If there's an even number, we'll put in a 0. If there's an odd number, we'll put in a 1. Right, so this even-odd digit is called a parity check. So this is our second type of code, right? It enables us to detect whether an error has occurred because we can come back later on, recount the number of ones in the first set of digits and compare to the parity check. Now, unfortunately, this doesn't tell us exactly which digit went wrong, so this code doesn't completely undo the error. It just flags when some error has occurred, and that's still useful. So the real code that classical computers tend to use for error-correcting memory chips and so on is only slightly more complicated than this, and it's a clever balance of digit efficiency and the ability to pinpoint the precise error location and correct for it. It's called the Hamming code, and if you enjoy mathematical puzzles, then I'd encourage you to go and look it up sometime. So this was all worked out back in the 1950s, back in the days of punch cards and vacuum tubes, when errors were rather more likely than they are on today's modern devices. Right? It enabled computers to evolve from just rerouting phone calls to do all sorts of things very effectively. Right? But one thing that they struggled to do, and they still do, is accurately simulating atoms and molecules, right? Chemicals, proteins, catalysts, medicines. So by the 1980s, this shortcoming was starting to be realized, and Richard Feynman, one of the more famous physicists of the last century, was one of the first people to propose what might be the solution. Now, the point he made was that nature is really quantum mechanical. It's not binary. And so you need a quantum mechanical computer. And I really love the excitement and the enthusiasm baked into the phrasing here. And by golly, it's a wonderful problem because it doesn't look so easy. So perhaps to get on to the quantum version of the transistor, the qubit, I'll have to teach you all quantum mechanics. Well, no, don't have to go that far. It turns out you can understand this stuff without calculus or complex numbers, but do be aware that there's some detail we're going to skirt around in order to get to the point relatively quickly. So, the qubit, the fundamental unit of quantum information. In some ways, it's like a binary digit. There are 2 computational states, and we can call them 0 and 1. Now, you might have heard that a qubit can be both a 0 and a 1 at the same time, right? Now, is this true or is it just nonsense? Well, what it is a simplification, but a fairly confusing one if we stop there. So let's dig a little deeper. As we did with the classical binary digit, we need to think about the physical system that's encoding this abstract information. Often we build a qubit out of a single atom, right? And we operate it so that these computational states, the quantum 0 and the quantum 1, they're related to opposite orientations of the atom's spin vector. Now, I realize that you might not know what a spin vector is, and then to you it's just an arrow that can point in some direction. And so, here we are, a 0 and a 1 at the same time. Right? It's just pointing to the side. So, for our classical transistor, the underlying physical thing was a voltage, right? One number, one parameter. And for our qubit now, under the hood, we have a spin vector, right? This arrow that can swivel around. And something we notice already is that this is more than 1 degree of freedom, right? Not only can we tilt up and down, but we can also turn around the equator. And so just like latitude and longitude on the Earth's surface, we have 2 parameters to define the configuration of this quantum thing that we call a qubit. And these are both fundamentally analog parameters, right? This north-south tilt and the east-west twist. And anything that the qubit experiences, either intentional as the result of a quantum algorithm, or accidental as the result of unwanted noise or interference, generally tends to change one or both of these parameters, right? Maneuvering the spin vector around in some way. So remember that the classical transistor dealt with errors with a margin for error. Can we do that here with the qubit? Well, sort of. You see, although the qubit's spin vector can exist being oriented to any direction, right? When we measure it, when we actually go and look at the state of our qubit, it collapses, right? This is the absurdity at the heart of quantum. The only results we ever see are North Pole or South Pole, right? Our computational states, this quantum 0 and 1. Well, fantastic, right? It seems like the margin for error is built in by the rules of quantum mechanics, automatic digitization of our analog quantum states. Well, unfortunately, it's not so easy. What happens with quantum mechanics is not that it collapses to the nearest pole based on which hemisphere you're in. No. The latitude only determines the probabilities of the two measurement outcomes. Right? As soon as we look, as soon as we go and really make the measurement, then ding, it collapses to north or to south. And if we repeatedly measure copies of the same quantum state, well, we see ding, 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 that this collapse, right, it's fundamentally random. There's no way to know what you're going to get. All we've got are probabilities and statistics, right? So we don't get a margin for error at all. What we get is probabilistic digitization, and that's significantly less useful. It's a bit like taking a color photo and turning all of the pixels completely black or completely white based on the darkness of that pixel, right? Statistically, it describes what was there before, but, well, you end up with a lot of black pixels scattered around what was a very light-colored sky. We also care about errors happening even before we measure and collapse the qubit, right? It's the fundamental analog nature of these quantum states that's related to the tremendous computing potential of a quantum computer. We need to keep access to all of the angle relationships between our spin vectors. If we just use the zeros and ones, well, that's a grainy black and white photocopy. No, we want to work in full high-definition color. And that means we need all the angles available to us. We can't be collapsing the qubits by looking at them. So what can we do? Well, we try the methods that worked for binary digits. Okay, repetition codes. Well, I need to take my qubit and make a few copies of it. Well, that's problematic, right? Because if I want to make a copy, I need to look at the original and ding, it collapses probabilistically, randomly to north or south, so it doesn't work. Quantum mechanics enforces a strict no cloning rule, and duplication just isn't allowed. So a few decades ago, physicists and computer scientists were really quite worried that quantum computing might be a non-starter, partly for this reason. By the mid-90s, we had a few ideas for applications other than just simulating nature. Code cracking, searching databases, optimization, but all of it was no good without some quantum-compatible kind of error correction. So what about the parity thing? Well, we can say that for a pair of data qubits, an even combination would mean aligned spin vectors, right? 0 and 0, or 1 and 1, but generally 2 arrows pointing in the same direction. And an odd combination could be 0 and 1, or left and right, right? Generally opposite directions. Okay, so I'm going to tell you we can take a peek at a pair of qubits. And you'll have to take my word for it that taking a peek is somehow different to a normal measurement. And it's really quite miraculous that we can do this without completely collapsing both qubits. But we take a peek at a pair of qubits to get a sense of their parity. And we entangle this parity into the state of a third qubit. Now, I don't say we put it into the third qubit because we never really had the result in our grubby little classical hands, right? We never looked at them. We just manipulate things so that their parity, right, the alignment or oppositeness, ends up encoded in the quantum state of our third check qubit by the rules of quantum mechanics. And I'll use the word entangle specifically for this kind of process. All right, but maybe our two data qubits are neither aligned nor opposite, right, with various angle relationships involved. Well, it turns out that the complete continuum of possibilities can be neatly encoded into the spin vector of the check qubit, right? For example, two arrows at right angles like this, well, we entangle our check qubit onto the equator, representing equal parts of even and odd parity. If you like, aligned and opposite at the same time. It's a lot to wrap your head around, right? But we can actually do this. This is what we do in the lab with real atoms. Now, it quickly becomes too complicated for simplified diagrams like this, so we're not going to dig much deeper. But we will briefly take a look at how we can use this quantum parity code to check and see whether there's been any error. So let's look at an example. We have our first spin vector oriented to the left, right? That's an interesting quantum state. And the second spin vector is set up in completely the opposite direction, pointing to the right. These are the data qubits we want to protect from errors. So we take a peek at the pair to discern their parity, and we entangle our check qubit with a quantum state representing this perfectly odd parity. After setting it all up, we measure out the check qubit, ding, and we get a classical 1, right? So we know at the start the parity of our two qubits is that they're aligned in opposite directions. That's the starting point. So now some noise gets in and messes up our spin vectors. For argument's sake, let's say a small angular tilt on one of them by about 20 degrees, right? That's our error. So we peek again at the pair, and this time the parity that we entangle into the check qubit is a little bit offset from the North Pole. And when we measure and collapse this, there are two possibilities, right? Most likely, ding, it collapses to the North Pole and we measure out a 1 just as before. It looks to us like there's no error at all, right? This measurement is reporting perfectly opposite parity. Now, at first glance, that seems problematic, but behind the scenes, it turns out that the small angle error has been erased, right, as part of the collapse of our entangled check qubit. Our two uncollapsed qubits are really back to being perfectly opposite, consistent with the result of our check qubit measurement. But there was another possibility, right? So we can rewind. And with the spin vector near the North Pole, we have got a small probability that, ding, it flips around to the South Pole and we get out a 0 instead, right? We would have to conclude that there's been a complete error, a complete change in the parity of the two qubits. And behind the scenes, there really was. Our uncollapsed qubits have now changed so that they're actually pointing parallel to one another. We can't be certain of the exact direction, but they're guaranteed to be aligned. So, do you realize what this is, right? It's no longer a probabilistic random collapse of the spin qubit state itself. It's a digitization of errors. We've gone from a situation where we had a small, uncertain error in an unknown direction into this situation where we've got either no error at all, which happens most of the time, or a complete 180-degree flip, which happens very rarely. And we know which one, right? That is super, super useful. There's not even any need for a margin for error, right? We keep the fully analog nature of the qubit, we keep the 2 degrees of freedom, and we keep complete tabs on when there are errors and when not. So it takes a few layers of nesting this basic approach to tie up loose ends and deal with some issues that weren't so obvious in the simplified example. But it all works out like a really satisfying puzzle. So 20 years ago, this was a theoretical triumph, right? But technology wasn't yet ready to test it out. And in the last decade, with improved capabilities to make qubits and to control them in this way, we're seeing that it does work like this in reality. Quantum computing is still in a noisy, intermediate regime of development. The probability of an error is generally too high at the moment for error correction to work well, in an efficient way. And there are generally too few qubits in today's devices. We tend to use them all up as check qubits, with none left to actually perform any calculation. Earlier this year, Google's quantum computing team made serious waves demonstrating that this quantum parity-based error correction really does work in practice. Now, they used 49 of their superconductor-based qubits, and 48 of those were check qubits. Yeah? Our work here at Sussex on trapped ion qubits is teaching us important things about the specific nature of errors in our quantum computers. How fast and in which directions the spin vector tends to be nudged most often, and therefore how best to tailor the error correction scheme. There's a long way to go before quantum computers can tackle world-changing problems, but we have a roadmap, and we're not only making steady progress improving the performance of the qubits, but we're discovering new shortcuts all the time in the form of better ways to apply quantum error correction. Quantum mistakes are complicated and they're unavoidable, but they can be fixed.